about the role oxygen plays right now. It's pumped into hospital rooms to save patients. It's the very first breath we take when we're born. We equate it entirely with life and survival. But go back 2.4 billion years, and this exact same gas was a highly reactive, lethal pollutant. In fact, it triggered one of the most devastating mass extinctions in our planet's history. Isotope records extracted from ancient rocks suggest this single chemical shift caused a catastrophic collapse, wiping out roughly 80% of the biosphere. Before this event, Earth was wrapped in a thick, smoggy blanket of methane. The only life forms around were microscopic anaerobic organisms that fed exclusively on chemical energy from the early oceans. To those original inhabitants, free oxygen was a totally alien, corrosive poison that ripped their cellular structures apart. The source of this deadly gas was a microscopic newcomer called Cyanobacteria, which emerged roughly 2.7 billion years ago. They possessed a strange new metabolic mutation. Instead of relying on scarce chemical nutrients, they used energy from sunlight to split water molecules and harvest the energy stored within those chemical bonds. But breaking water leaves behind leftover atoms. The cyanobacteria cast off this highly reactive waste into the environment as molecular oxygen. This microbial process represents the first global pollution crisis, a catastrophe of planetary chemistry triggered by billions of organisms venting metabolic waste into the sea. If cyanobacteria started pumping out oxygen 2.7 billion years ago, you would expect the biosphere to die off immediately. Yet the extinction event didn't happen for another 300 million years. The delay happened because the early oceans contained a massive geochemical buffer. The water was heavily saturated with dissolved iron, acting as a planetary sponge. As soon as the cyanobacteria produced free oxygen, it reacted with that dissolved iron. It literally rusted the oceans, raining solid iron particles down to coat the seafloor in thick, heavy layers. This chemical reaction soaked up the toxic waste for hundreds of millions of years. The sheer volume of rust that sank to the bottom is the exact same material we dig up today from massive open-pit mines to build our global steel infrastructure. The Earth was silently absorbing the pollution as fast as the bacteria could produce it. But that iron supply was finite. Eventually, the iron ran out. The sponge was full. With the buffer gone, free oxygen began bubbling out of the saturated oceans and accumulating in the atmosphere above. For the anaerobic organisms living on the surface, the exposure was devastating. Oxidative stress meant the highly reactive oxygen atoms stripped electrons from their bodies, physically tearing their genetic material and cell membranes apart. While the biosphere was burning, the atmosphere was undergoing a violent chemical reaction. The rising oxygen collides with the methane that had been acting as Earth's primary thermal blanket, breaking the greenhouse gas down into water and much weaker carbon dioxide. Without that thick methane blanket holding in the sun's heat, global temperatures plummet. This triggered the Huronian Glaciation. A Snowball Earth scenario entombed the entire planet under thousands of feet of solid ice for millions of years. The Great Oxidation Event was a dual-front apocalypse. It simultaneously sterilized the biosphere with a corrosive gas and locked the survivors in a planetary deep freeze. The post-apocalyptic Earth was a frozen wasteland with a newly toxic, oxidizing atmosphere. Life only clung on in microscopic, isolated pockets, hiding deep underwater. To venture back out, surviving organisms were forced into a brutal evolutionary gauntlet. They rapidly evolved specialized enzymes like catalase, whose sole purpose was to disarm and neutralize reactive oxygen molecules before they could cause cellular damage. This chart compares the modest energy yield of anaerobic metabolism to the massive output available through aerobic respiration. By burning nutrients with oxygen, these microbes generated a surplus of energy that changed the limits of biology. Instead of merely building a shield against the poison, life figured out how to ingest it and use it as high-octane fuel. This surplus energy allowed for a process called endosymbiosis, where one cell absorbed another, transforming it into a permanent internal engine called a mitochondrion. By integrating these aerobic power plants, cells could generate more energy than they consumed. These high-energy, complex cells provided the biological foundation for multicellularity. Life finally had the power required to build specialized tissues, organs, and eventually the complex animal bodies we see today. This satellite image maps the concentration of ozone in our modern atmosphere. That layer formed anciently when the excess oxygen gas bonded together high in the stratosphere. It created a UV shield that finally allowed this new, complex life to safely leave the oceans and colonize the dry land. The existence of every complex organism on Earth, including humans, isn't the result of a gentle evolutionary curve. We are the direct, surviving legacy of the greatest pollution crisis in planetary history.